Working properly. In case you didn't see, it only took audio on Tuesday, and I think I have it fixed, but I'm not 100% positive, but we have to get started. Today, we're going to finish up 2D vectors, then we're going to go over functions. I know there was a lot of participation activities for today. And you have until the end of the week this week to get them done. So you have until tomorrow night to finish them all. That's not normally going to be the case, but I just decided last night in looking at how many there were that it would be difficult to get them all done. Functions are definitely something that gave many of you trouble in 102, so it's important that you get up to speed with them. I'm just going to touch on a few of the important things with functions today, and you're responsible for everything in both the lecture notes and in chapter 6, but I'm just going to hit on the things that I think are embellishments of what we talked about in 102. Like section 6.1 to 6.5 are pretty much just review of what we did in 102. I'm not going to really spend a lot of time covering them other than to have you work a quick function today. To kind of get you back into practice. So 2D vectors, finishing them up, and then we're going to talk about functions. So last time I finished by talking about two ways that you could approach the V-flip part of Lab 2, the program where you're going to flip a PGM image, turn it essentially upside down. And today I want to show you a third way that you could do it, which is the most inefficient way to do it. And it's going to illustrate a point that was also made in the lecture notes about the danger of inadvertently copying memory without really realizing you're doing it. So you may remember that the way you create a 2D vector is to either do it this way or hopefully in labs yesterday they covered type defs, correct? Very good. So you could use a type def here as well. Right now I'm not, I'm just doing it this way. So this is a PGM file. And here's a third way to do it. I showed you two ways last time. So I'll assume that you've already read in the rows and the columns so that you have that information as well. And we'll have some loop variables. So we could say again PGM dot, actually we're not even going to say PGM dot resize this time. We're simply going to say for r equals 0, r less than rows, r plus plus, and we're going to actually use a vector here, a 1D vector, to keep track of each row. So we'll say pixel row. So what we're going to do is read in a row of pixels and put it into this vector that we call pixel row. So before we do anything, as we come into the beginning of our thing, we clear pixel row so that we empty it out and it's empty. Then we're going to read pixels into it. Well, actually, and assume that I've declared a data value called pixel. I'm not going to do it here, but just assume I did. Okay, so at the end of this, I have a row of pixels that has been read into this 1D vector called pixel row. And what I can now do is I can push this pixel row onto PGM using pushback. And that works because PGM is a vector of 1D integer vectors. Okay, so going back up here, you can see that PGM is a vector of 1D vectors and pixel row is a 1D vector. So I'm just pushing back pixel rows. So in this case, I didn't have to resize PGM before I started the for loop like I did previously, because I'm simply going through that outer for loop rows number of times. So when I'm done, I'll have rows, number of rows in my PGM. So this is a third way you could write the for loop, and it is the least efficient and the way that you could get points deducted. Okay? Now, the question is, why is this particular way of doing things less efficient than the other two approaches? The reason is right here. Okay, this statement right there. What it is doing is it is creating a completely new copy of pixel row and then adding it to the PGM vector. It is not simply assigning it's not simply assigning values from pixel row into PGM. It is literally creating a new 1D vector and copying the contents from pixel row to that new 1D vector. And that is inefficient. Okay, having to allocate that new piece of memory and then do the copy operation is slowing this program down. So you don't explicitly see in this program or in this statement this copy operation taking place, but it is. And it's important that you be aware that these copy operations can be occurring so-called under the hood, and they are inefficient and they are slow. And if the vectors are very large, if this was a large PGM file, okay, so if this was a photo image, the photo images these days are pretty big, right? They're several thousand pixels by several thousand pixels. So the vector could be a several thousand pixel vector that we're copying. So you need to become familiar with times when copy operations are being performed. And pushback is a copy operation. Now when it's copying a single integer, which is what was happening with my second approach, that's a very cheap operation. Copying one integer is very efficient, but copying an entire vector is incredibly inefficient. So be careful. This statement is inefficient because it is copying an entire vector. So please don't do it this way. Okay, and we'll give you more examples as the semester goes forward where something like this happens. Okay, so what this approach does illustrate is a third way to flesh out a 2D vector. Remember from last time, when you declare a 2D vector, it's completely empty. It's a 0 by 0 vector. and you have to flesh it out. Last time I showed you two ways to do it. I fleshed out the outer part, the rows part, by resizing, and then in the inner part, I either used pushbacks to flesh out the columns, or I used a resize on each individual one. Here, I'm using pushback on both dimensions. So you've seen three different ways that you could flesh out a 2D vector, because when it's first declared, it is 0 by 0. Okay, and the other important thing to remember is, like arrays, 2D arrays, 2D vectors should be considered in row major order. So the outer loop is the row and the inner one are the columns. Okay, so questions about them? Okay, let's move on to functions in that case. So you may remember from last time, well, let me actually motivate it with an example. So I'm going to go back to the full palindrome problem. So you may remember from the full palindrome problem that we read it, or we took a string as input. And actually you've already seen functions in Topcoder, because in Topcoder you're writing a function. In this case it was one that returned a string, and it took a string as a parameter. Okay, and you were determining whether the string you took as a parameter was a palindrome, a full palindrome, or not a palindrome. You may remember that we kind of duplicated one piece of code. So initially, this piece of code was used to check to see whether W was a true palindrome or not. Basically, we started two indices, one at the left end and one at the right end of the string, and moved the two indices toward each other. And as long as the values on either end of the string were the same, we continued. But if we ever discovered that the values at the two ends of the string were not equal, we knew it wasn't a true palindrome, and we exited the loop. Then we had a piece of code that simply removed the repeating characters from W and created a new string T, and we did essentially the same code with T with palindrome checking. We had I and J at either end of the string, moved the two indices toward each other. As long as the values at either end of the string were the same, we continued. But if they were not equal, we knew it was not a palindrome, and we returned not even full. Well, you may have remembered that Dr. Planck in his notes said this is kind of icky. And the reason it's icky is because he repeated his palindrome checking code twice. And that's not good programming practice. One reason it's not good programming practice is, let's say he later discovered a bug in his palindrome testing code. And he went in and he fixed it for the code that checked T. But he forgot to check or to modify the code that checked W. Well, the bug would still be in the code that checked W. So if you duplicate the same piece of code multiple times in your program and later find a bug in that logic, you have to remember every place in the program where you duplicated the code, and you need to modify each copy of the code, which is time-consuming and error-prone. And it's worse still if you're no longer the original writer of the code. Once the code goes into production, there's a good chance someone else is maintaining the code, and they may not realize when they find the bug, say, right in here, they don't realize perhaps that there's a second piece of code that duplicates this code and that it needs to be fixed somewhere else. So it's very dangerous to have duplicate copies of code. Well, functions are a way to prevent that. A function performs a task, and because you can give it parameters, it can be customized on different sets of parameters. So what you really want to do in this case is create a single function with one copy of the code that does palindrome testing, and then call it once with the string w and the second time with the string t. So the right thing to do would be to duplicate the code. So there's about 8 lines of code. So one thing you can do with VI, you may not have learned yet, if you want to copy a chunk of code, you can count the number of lines. So Control G will tell you what line number you're on. So I'm on line 32. Now, I want to copy up to this piece of code, which is line 38. So there's Control G gives me the lines. Now I know I want to copy 7 lines, so I'm going to do a command here, 7cc. It's going to copy 7 lines into, actually, that's not going to work. Sorry. I want to do 7 yank. So I yank 7 lines. So it's actually 7YY. So I yanked 7 lines into my clipboard. Now I'm going to go up and I'm going to write a function that checks to see whether it's a palindrome. It's going to take a string, going to say S. Okay, I have to remember to declare I and J. I have to do some modifications here. So remember, if you read it's section 6.7 today, common errors in writing a function. I have to be very careful as I copy and paste here that I change everything. In 6.7, they're talking about how it's very easy to forget to change variable names. So I do have to make sure that I'm careful about changing variable names. So I'm changing the T to an S because I'm now checking an arbitrary string S. It's fine to say I and J, but I need to remember now to be testing the ends of the strings S and I. I'm no longer going to return not even full in this case. What should I return if S of I is not equal to S of J? False, because it's not a palindrome in that case. Okay, and if I get to this point where I exited the loop, what should I return? True, because if I get out of the loop, it meant that I never discovered an inequality, which means that at all times the conditions for a palindrome were satisfied. So having dropped out of the loop, it must be true that it is a palindrome. Okay, so now I have my isPalindrome function, and I can go back and I can delete all of this code that was doing palindrome testing. So I'm just going to call isPal equal isPalindrome on W if isPal return palindrome. Okay, otherwise I still need to create my T function, but once I'm done with that, I again am going to simply call again isPalindrome on T. In fact, I don't even need to save it. I'm just going to say if isPalindrome of T, what would I return? You remember? What type of palindrome is it? A faux palindrome. And I may be getting this slightly wrong. I think it's return not a palindrome. Something like that. Okay, so this code is also somewhat easier to read. So I've made the main function shorter. It has three main parts. First, test to see whether the original string is a palindrome, and if it is, return palindrome. And I could have simplified even that. I could have simply said like that, and that's perfectly fine. Then in this code, I created my string with repeating characters removed. And finally, I checked it to see whether I had a faux palindrome or not a palindrome. So the logic even is a little easier to read by having used a function. And instead of repeating the same code twice, I have only one copy of that code. And should I find a bug in it, I know that once I've fixed the bug, it's fixed for all palindrome testing in my program. So this actually shows two reasons for using a function in your program. One is to avoid duplicate copies of the same piece of code. And two, it simplifies the logic of your main function by moving some of that code off to another function. You know how in an English report you sometimes use appendices, right? So that someone can focus on the main point in the main body, and then if they want the details, they go to the appendix. Functions are a little like that. Okay, so the main body says, okay, if you want details, go out and look at this function, but you kind of know what the function does. So if you don't care about the details, keep reading. Okay, so it simplifies logic, and it segregates a piece of code in one place instead of having multiple copies. Okay, and the important things with the function, it has a return type, so it computes a value, and it returns that value via a return statement. The return statement does not have to be in the last statement. If you know your result before the end of the function, you can return it as soon as you know the result. Then you have the function name. And then you have parameters. And you can have more than one parameters. If you do, they're comma separated. And the parameter allows you to allow it to be customized for different values. So in my particular case, I used it once to test the string W and once to test the string T. Important point is that the name of the parameter does not have to match the name of the argument, because that's what gives us flexibility. So here I pass W. Okay. Later, I pass T, okay, but I used as my parameter name S. Okay? And also remember that the scope of a variable is limited to its function body. So some of you in 102 would try to do things like declare it as W, and you would somehow magically think that as long as the argument had the same name as the parameter, that any changes you might make up here, now I know up here I didn't make any changes, but you would think that if I changed this to say foo, that magically the W down in the calling function would change to foo, and that's absolutely false. And we'll get into that a little later. Okay, so in general, when you write a function, the parameter names, in fact, will not match the names of the arguments in the call. Okay? So questions about any of this? Hopefully this is review. So to warm you up, now that you've seen that, for those of you who have the book or your laptops with you rather, there is a exercise from section 6.3 that I'd like you to do. It is 6.3.4. If you don't have your books, I'll just put it up. So it's participation activity 6.3.4, temperature conversion. Okay, so what you're being asked to do is complete this program. There's two places. If you look at line 5, it wants you to write a Celsius to Fahrenheit function. And on line 15, it wants you to call that Celsius to Fahrenheit function. And over on the right-hand side, you can run it to see if it works. So I'm going to give you about 5 minutes to about 10:19 to let you try to write that function and to call it. Feel free to work with a neighbor and talk. And if you have a question, feel free to raise your hand, and I will circulate and answer questions. Let's take a look at how we can do this. So here would be, so we want to define a function, Celsius to Fahrenheit, and I know it didn't tell us what type of value to return, but you can kind of figure it out looking at the variables. So what kind of value do you think it should return? An int or a double? A double because the variables temp F and temp C were declared as doubles. So you can make an inference that it should be a double, and also that it's going to be taking a double, which is a variable I will call Celsius. Okay, and it should return. Okay, I'm going to start by, I know that it is 1.8 times Celsius plus 32. So I'm going to do it like that. And then down here, it's asking to compute the new value, so it's temp F is what's getting the result, and I'm going to call it, so I call it with the value temp C. Okay, and if I run it, I get the right result. Now, there's a pitfall here. Okay, I knew it was 1.8, but most of you know this more familiarly as the formula 9/5 times Celsius plus 32. Okay, watch what happens. Does that look right? No. So what happened? Why did it all of a sudden go wrong? 9 divided by 5 is the right, that's the formula. It's a classic formula. Yes, Ryan?
The issue lies right there because you're doing integer division.
Very good. So because both of the operands to that operator are integers, it's performing integer arithmetic. It doesn't care that later on it's multiplying by Celsius, which is a W. That's irrelevant. All it looks at are the two arguments to that particular operator, and the two arguments are both integers, so it performs integer arithmetic. And 9 divided by 5 doing integer arithmetic is 1. So then it multiplies 1 by Celsius, which is 100, and it gets 132. So probably many of you are rusty and will easily forget that little anomaly, but you need to remember it. Now watch something, because this can really be, some of you might have written it like this. It works. But wait, Dr. van der Zanden claimed that the two arguments were integers. So it should be the same. It should be 132. Dr. van der Zanden lied. But he didn't. Why didn't Dr. van der Zanden lie? Yes.
Because you're multiplying by the multiplication goes first. So.
Very good. The multiplication takes precedence here because it is the first operation we perform. Because when we have equal precedence operators and times and division are equal precedence, the times here is evaluated first, left to right. So there, the multiplication is done first, and since Celsius is a double, it performs a floating point multiplication and gets a floating point result. Now, when it divides by 5, we're dividing a double by an integer, and it performs floating point arithmetic. So for our mathematicians out there, what does that tell us about commutativity in a program? Doesn't exist. Okay, so unlike in math, you don't necessarily have commutativity in a computer program. So order of operations can be important. Okay, so if I wanted to really write it the way it's often written, how might I have written 9 divided by 5? 9.0 divided by 5 would have worked. Okay, so just make sure that you're up on what is integer arithmetic versus what is floating point arithmetic and when each is going to happen. Yes, Ryan?
Is this little afterthought? Why does point the 0 get truncated even though it's a double?
So remember that if you have a result that is floating point but is 0.0, it truncates it unless you have that show point directive. Remember, it's probably in the midst of your memory, but there's a show point directive. Okay. So without that show point directive, it assumes you don't want the 0.0 because it's kind of extraneous. So if you really wanted it, I could have said, may not let me, let's see if it does. I may not have, it's not going to work because I don't have the formatting directives in there. Okay, it's not going to work because I would have to include an IO manip. Pardon? Oh, you can? Okay. Include, thank you. Okay. Voila. And now I could say set precision and fix to get it down to 1. Okay? Other questions? Yes?
When you find Celsius,
Mm-hmm.
should you also declare it as a constant in this case?
You could. That's a good question. So we're going to get to that. So good form. This really gets into some religious wars. Good form would say, yes, I should declare it as a const because I'm not modifying it, and it's kind of a form of documentation that tells any maintenance programmer that I really didn't mean to modify it. I find it to be ugly, okay, and aesthetically unpleasing. So I'm not going to bust your chops over it. Most of the professors here won't bust your chops, but some of the TAs might get in a tizzy. But so for those of you who didn't read the book today or forget about it, const is a thing you can put in front of a parameter to say that this value will not be modified in the function. And it's both documentation. It tells everyone looking at the function it should not be modified. It's also an aid to the compiler. Sometimes the compiler can perform optimizations if it knows that the variable cannot be modified. Now that said, when C was developed in 1980, compiler optimization technology was a lot more primitive than it is 35 years later. And it's kind of superfluous these days because a good compiler should be generally able to determine whether it is constant or not. So really, const was in there in the first place as a compiler directive to help the compiler with compiling. Later, it kind of evolved to, well, it's kind of nice as a programming practice, but that wasn't the original purpose of const. The original purpose of const was as a compiler aid. Okay? So, just a little history. So yeah, I'm not going to be really up in arms if you don't use it. Other questions? Okay. So, moving on. Hopefully in 130 you learned about how functions work, but boy, gosh, if you didn't, you're going to learn now. So, it's important that you know how functions really work. Okay, and I know I had you do this participation activity, but it's so important, I'm going to show you how to do it again. So when you declare your functions, actually this isn't it though, this is it, how function call return works. So when a function is entered, the compiler allocates what is called a stack frame for that function. So this is a stack frame for main, and this is a second stack frame for find max. So on the left, there's a function that simply finds the maximum of 2 integers and returns it. And when a function is entered, as I said, on the stack, there's a stack that keeps track of all local variables. So remember, local variables are variables declared within a function, and they include the parameters to that function. So main has 3 local variables, x, y, and z, and therefore it has 3 local variables in its stack frame. Similarly, find max has 2 integers, a and b, plus it has a local variable m, and therefore it has 3 variables allocated for it, a, b, and m. Now, the stack frame is not allocated statically when it's compiled. It's allocated only when the function is entered. So this is showing the state when we're actually in find max and executing it. Okay? Now, there's also an area of your program where the code is kept, and it uses assembly language instructions. Okay, so over here is our assembly language instructions. So at location 3 in memory, so memory starts, and in this case the program was placed in location, starting at location 3. So there are 3 assembly language instructions to set x, y, and z to 0. And you can see that in fact they were allocated at memory locations 96, 97, and 98. Now this is a little bit of a lie. Hopefully in CS130 they told, why is this a little bit of a lie? Why can't y actually be stored at location 97? Pardon? Actually by 4, because integers are 4 bytes. So really, the location would have to be 100 because there's 4 bytes required for each integer. So this is a bit of a simplification, as long as you know. Yes?
Memory handle that as
No, it doesn't. So there's more than one simplification here too. No, it doesn't. So I know what you're talking about for the calculations under the hood, but physically in memory, it's 96, 97, 98, 99 is allocated to X. Then 100, 101, 102, and 103 is allocated to Y. So if you actually looked at the physically mapped memory, it's 4 bytes. Now, if this was an array calculation, it would do some fancy stuff for you. But this isn't an array. Yeah. Okay. So this is just, I want you to know this is a simplification of memory. Okay. So then there's instructions for the CN statements, CN into X and CN into Y. Okay, so there's some assembly language instructions to do that. Then there is the instructions to copy right here, the instructions to copy X and Y down to their respective memory locations. So that is called call by value, where we copy the values of the arguments to the parameters. Okay, and then we set a return address in this new stack frame. So here's this new stack frame, and we need to know where to return to, which is to memory location 31. Okay, because that's where we're going to assign the return value to Z. So one of the things that my called function needs to know is where to return to. So 31 is the return address. So that's also put in the stack frame. Then there's a jump statement to location 50, because at location 50 we find the instructions for find max. So at location 50 is where the instructions for find max start. Then after the function call we have the assignment statement, so we need to set Z to the return value. So in this case the return value is at location 102, and the return value is M. If you look at find max, you see return M. So the compiler knows that the return value is at location 102. So it copies the value from location 102 to location 98. Then we have the instructions for cout. I have no idea why that instruction is there, because this is not a loop. So that shouldn't be there. Okay? The only reason I could think that it's there is that they thought that the entry location for the program is at instruction for 40. That's the reason, fine. But normally the entry location is 0, so I just don't understand why that jump 7 is there. This isn't a loop. Okay, so then the instructions for find max, hopefully you can understand. We don't have to go through all that, because I don't have all day, and neither do you. So if we actually compile it, you can see what the compiler does is it goes through one at a time, and it's adding at each point instructions. So here it's adding the instructions to copy. Now it's adding the cout instructions. Now it's compiling find max, blah, blah, blah. Now if we run it, and I know it's a bit fast, so you may have to do this on your own time, but if we run it, it's going to execute these instructions and set these variables to 0. Now it performed the read. Now it's copying them down to A and B. Now it's setting the return address, jumping to location 50 down to here, where it's executing. Found the return value, which is 888. Now it's going to copy it back up here into Z. There we go. Now it comes down to the cout, and it prints it out. And that's it. It terminates. So questions about that? What's really important is that you understand this notion of stack frames, that as each function is entered, a piece of stack frame is allocated on the stack that's large enough to accommodate the local variables and a return address and a return value. But for your purposes, you really only have to know it's enough to accommodate local variables and parameters. When the function exits, the stack frame is popped. It's removed, and that memory disappears. So when find max returns here, this memory goes away. And all that is left is the memory for x, y, and z. So when it returns, you can't just say, oh, let's print out A. A is no longer defined. In fact, it was never defined within the scope of main. The only thing defined within the scope of main are x, y, and z. A, B, and M are defined within the scope of find max. And the two can't look at each other. They're like black boxes with no windows. Okay? And when we made the call, we copied the values of x and y to A and B. A and B could not directly modify x and y. Okay? Now that's sometimes inconvenient. Yes?
Were you going to say reference variable?
Yes. Okay. So sometimes that's inconvenient. Sometimes we want to be able to modify the original arguments. For example, classic example. Let's say I want to write a swap function. Okay? Now remember, sometimes we don't want to return a value from a function. When we don't, we use the return type void, which says we're not returning a value. And instead of calling it a function, we sometimes call it what? There's another word. Not method. A method is actually associated with a class. And a method can return a value. Procedure. Okay? I know that you may not have remembered, but sometimes you'll hear, especially crusty old-timers, talk about procedures versus functions. Procedures, when they say a procedure, they mean it has no return value. And when they talk about a function, they mean it has a return value. Now, in fact, but procedures are also functions. They simply return no value. They return void. So what I want to do is I want to swap x and y. So I need a temp value for that. And then I set x equal to y and y equal to temp. Okay, and in main, I'll declare two values a and b. I'll read into a into b. I'll swap a and b. Now I'll print out a and b. Okay, so I'll compile this. Do we agree it swaps x and y? In fact, let's do it to verify it. Let's verify that the swap happened. So remember, a good thing for debugging are print statements. The other good thing for debugging is GDB. So don't forget about GDB. Okay, so let's compile this and run it once it gets done thinking about compiling it. So I'll enter 10 and 5. Okay, so before x was 10 and y was 5, afterwards x was 5 and y was 10, but there was no swap. A is still 10 and B is 5 at the end. Okay, we can verify that. Let's do before and after here. Okay, before A was 10 and B was 5, and after A is 10 and B is 5. So even though X and Y were successfully swapped, A and B weren't. Okay, and the problem is that the values of A and B were copied to X and Y, and X and Y did not change their arguments. So whatever happened in swap stayed in swap. Less like whatever happens in Vegas stays in Vegas. But that's not what we want. We want what happened in swap to affect A and B. So to do that, we use what is called a reference parameter, and we put an ampersand in front of X and Y. So these are called reference parameters. They have an ampersand in front of them. And when you put an ampersand in front of it, any modification you make to the local variable is reflected in the calling argument. So it becomes, in effect, an output variable. And you might remember that what really happens is instead of the value being copied from A to X, it actually copies the address of A. So, in fact, if this were main, and the address of A was, say, 96, and the address of B were 97, and this is swap, and this is X, and this is Y, at locations, say, 200 and 201. What really gets stored here is 96 and 97, which are the addresses of A and the addresses of B. And then when we access X, what really happens is we go to address 96, which is really the memory location for A. So reference parameters actually copy an address. They don't copy the value. And that will be important in a moment. Okay? But right now, just remember reference parameters are the way that we allow a local variable to change its corresponding argument. And that reference parameters actually cause us to copy an address of the argument rather than the value of the argument. So let's go and run this now and show you that it works, that I'm just not telling you a fairy tale. Okay, and there we go. Before A is 10 and B is 5. Afterwards, A is 5 and B is 10. Now, quick review of command line arguments. Let's say we did this with command line arguments. Okay, so we say int argc char star argv int ab. Okay, quick question. Can we do this? Is this going to work? No. Why not? Because those are strings. Even though we'll input them as integers, they will come to us as strings. Okay, so to fix that problem, we would have to declare an iString stream, and we would have to push argv1 into there. Then we would, dot string argv1. Then we would read it into A. Then we would clear it. Very important. And put argv2 into it. Okay, and it should work again as long as I include string streams. I could avoid that apostrophe. So you see what I did here. I created this buffer, stuffed argv1 into it, read it into A, cleared it, stuffed the second command line argument into it, read that into B, obviously didn't do any error checking, which I should, and voila, it works. Okay? Let's say I forgot segfault. So always important to check to make sure, that's why it's so important that you check to make sure that you got the expected number of arguments. Okay, let's say that I said swap Brad and Fred. It didn't work so well either. That's why it's important we make sure the user entered valid input. So I know it's a pain in the neck, but you need to do it. Quick question, why did I start at 1 rather than 0? I'm always telling you that arrays start at 0, yet I started at 1. Yes? Very good. The first command line argument is the name of the program and is pretty much useless to us. So argv0 is the name of the program. And in fact, Java found this to be so useless that it didn't even include it in its arrays. So in Java, command line argument 0 actually starts with the user command line argument. So this is, argv0 is kind of like the appendix. We no longer need it. Okay, I got 5 minutes. Don't be packing up yet. See some of you wanting to pack up. Not done. Okay, so we move on to the concept of functions with string and vector parameters. So you will remember that I said it's really, oh, good, yes. Yes, there is a efficiency advantage, which we're about to talk about. Okay? So if you're passing large structures to a function, such as a string or a vector, then you want to always pass them by reference. Because if you pass them by value, they'll be copied. Okay? And going back to my rant from at the beginning of the, not rant, but beginning of the class, copying a large vector is inefficient. So we don't want to pass vectors by value. Instead, we always want to pass vectors by reference so that we pass just the address of the vector. So in fact, when we pass vectors or strings, you should try to take care to pass them by reference. Now, I always forget to pass strings by reference. Is that a big deal? Probably not, because strings aren't usually that big. So I'm not going to put a lot of emphasis on passing strings by reference. If you can remember to do so, please do. It's good practice. But it's not the end of the world to forget because strings aren't that big. In fact, the book makes some comment about if this structure has fewer than 10 elements, feel free to pass it by value. If it has more than 10, pass it by reference. That's arbitrary. Okay, much better is to always pass vectors and arrays by reference. But remember, arrays are automatically passed by reference, so you don't have to do that. But vectors, good rule of thumb, always pass vectors by reference. If you can remember, try to pass strings by reference, but it's not the end of the world if you forget. Okay, so that's really the whole point of 6.10 is telling you to always pass strings and vectors by reference because they're large structures, and if you forget to pass them by reference, they'll be copied, and that's a waste of time. Now, Of course, if you want to modify them, it's doubly important to pass them by reference, because if you don't, then when you come out of the function, the copy is thrown out along with its modifications, and the original argument is unchanged. So, and oftentimes when you pass a vector, you really do want to modify it, so that's the second reason. Now, gentlemen, what was your name again? Yeah, Preston. Preston asked earlier, should we declare something that's const? Sometimes with vectors, there's a stronger argument to be made for declaring vectors that aren't to be modified as const. And the reason is, since we're passing them by reference, any modification to them could in fact affect the main program. Therefore, if you really want it to be const, to tell a maintenance programmer, really, this is supposed to be const and not changed, there's a better argument for declaring your vectors to be const vectors. So here, they declared it as const because they didn't want it to be modified. Again, will I bust your chops for doing it? No. Now, one of your TAs, Adam Howard, tends to be a little more of a hard ass about it. So, I'm not sure, but I know he's a little more of a stickler for these things. So you may find an issue with him if you don't declare stuff const. Okay, just warning you. Okay. I have one more minute, and I'm going to make good use of it because there's one last thing I want to talk about, which are function prototypes. So thus far, I've always put the function above main. Okay? Do you put appendices before, at the beginning or end of a report? You put them at the end. In general, we put functions at the end of our program, not at the beginning. Usually main is our first function. So let's do that. I'm going to put swap at the end. And I'm going to recompile it. Oh, come on. That can't be working. Unbelievable. Wow. The way it should be. It's a two-pass compiler. Okay, I'm not going to get into what the difference is between a two-pass and a one-pass compiler, but C traditionally is a one-pass compiler, and that means that on the Hydra machines, you're going to have to do this. You need to declare your functions before main as function prototypes. You don't put the function body there, just the function declaration, and then you put the function definition after main. And this puppy is called a function prototype. So, we will pick up with classes and their ilk on Tuesday. Good luck with Lab 2. Lots of TA support today and tomorrow, so try to wrap those up.
Good question.